The following example aims at determining the independence of pairs of events. So, when rolling a six-sided die, consider the following events. Event A, rolling an even number. Event B, rolling a multiple of 3. And event C, rolling a prime number. So now we have to verify if each pair of events is independent. So we have to check if A is independent from B, B from C, and also A from C. If you remember, the way for us to verify if a pair of events is independent is given by the expression that states that the probability of the intersection of two events, if they are independent, equals the product of their individual probabilities. So this will be our guideline when addressing this question. So on one side, we need the probabilities regarding the intersection of the events. On the other side, we need the individual probabilities, and we will start by the right-hand side. So, in order to determine the probability of A, B, or C, first we need to see what is the sample space for this situation. And when tossing a six-sided die, the sample space includes 6 outcomes from 1 to 6. So within this sample space, event A, which consists of rolling an even number, can also be defined as a set. And within this set, we have outcomes 2, 4, or 6. We have 3 outcomes. For event B, rolling a multiple of 3, we have 2 outcomes, 3 or 6. And finally, for event C, rolling a prime number, we have 3 outcomes, through 3 or 5. So, defining these 3 events as sets allows us to calculate the probability for each one of them. So the probability of A is given by the ratio between the favorable outcomes and all the possible outcomes for the experiment. So it is 3 divided by 6. And the probability of B will be 2 favorable outcomes divided by 6. So this is the result. And finally, for event C, we have also 3 divided by 6. So this is the result. So now that we have all of the individual probabilities, we need to calculate the probabilities regarding the intersection of events. So as we have represented each of the events by sets, we can also represent the intersection using a set. So if you calculate the intersection between A and B, the intersection will pick up only the common elements between these two sets. So the only common element is 6. And then if you calculate the intersection between B and C, for example, between B and C, you only have one common element, which is 3. And finally, between A and C, you have one common element, which is 2. So this way, you can also calculate the probabilities regarding the intersection. So for each one of the intersections, you only have one favorable outcome within 6 possible outcomes. So you can calculate the probability for each one of the intersections. Now that you have all the values for all the probabilities, you need to apply them to the expression and check if the pairs of events are independent or not. I'll try it with A and B, and I'll leave you to try it with the following pairs, okay? So I'll apply the expression to events A and B. So this means that the probability of the intersection must equal the product of the individual probabilities. So if you remember, the probability of the intersection is 1 divided by 6, probability of A 1 divided by 2, and B 1 divided by 3. So we get 1 divided by 6 equals 1 divided by 6. So this is a true proposition. So what can we conclude from the fact that this is a true proposition? We can conclude that A and B are independent. So I'll ask you to check B and C, and also check A and C.